So welcome to the 9th Geopolymer Camp. Like every year, I'm presenting what I call the state of the geopolymer research and development. That is what I consider to be important on all events or publications that happened this year and last year. We had this year a webinar on the internet, and we had a relatively high number of participants. I would like to ask you, if you have not done it, to look at our technical library on the internet, because you have several technical papers to download that are very important, as well as archaeological papers. Same for videos. As I told you, all Geopolymer Camp keynotes are on videos. We have 8 videos that last 1 hour, and we have 11 videos. All the keynote speakers are also recorded. So you'll find with the videos a lot of interesting topics. The webinars, we made live recording of the webinars, and we have 12 videos available that tackle every details on geopolymer chemistry. And we have the 3 important videos on my campaign, why alkali activated materials are not geopolymers. Especially for this campaign, part 1 that we put on August 2014 have been watched at our Geopolymer Institute site more than 14,000 times. And you find it on YouTube. This had been put later. Part 2 that we put on 2015 has been watched more than 6,000 times, cryo-frame statement and historicity. And our part 3, what scientists are now writing on this issue, have been watched more than 2,600. These are excerpts of my keynotes. Today, I will present the topic from theory to global industrialization. What are geopolymers? They are geopolymer binders, resin, paint, coating, grout, geopolymer foam, geopolymer cement, geopolymer concrete, geopolymer carbon composite, and geopolymer ceramics. If we look at the representation of our Metakaolin-based, silicon-based geopolymer, the rules are based on the ratio SiAl, 1:1 SiAl, 2:1. These are concrete, cement, and bricks applications. If we increase the ratio SiAl, we increase the polymeric character of the system, and we end up into the applications for industrial heat-resistant toolings and the like, and fire protection. And by increasing, we enter into high-tech applications, including composite, geopolymer composite for high aeronautic, or this is only on research, but for racing cars it is running perfectly. I started geopolymer research. At that time, it was not geopolymer, it was just an idea, in 1972. I had been shocked by a terrible fire that we had in France in the 1970s that involved in a nightclub. More than 150 people were killed because of the plastic decoration that was used at that time in the nightclub. So it was a shock for all people like myself. I am My background is organic chemistry, and I was an expert in organic polymers and plastics. So we raised the questions. Plastics are dangerous. Are organic polymers heat resistant? Nature states only minerals provide fire and heat resistance. So my target was to create inorganic polymers. Geopolymers are polymers processed like organic polymers, yet they are geopolymers, that is fire and heat resistant. And you'll find in my chapter 22 of Geopolymer and Chemistry and Application book, a chapter dedicated to fire and heat resistant geopolymer form. We had a licensee that was a German chemical company in the 1980s that had had a small startup called Trollit. They developed foamed materials. They created the company, and they closed it 5 years after because their materials were too expensive compared to cheap plastic at that time. 30 years later, I guess you have seen these pictures in the news. So this is the reality. 30 years long, nothing happened. So that we did not concentrate on this fire application because nobody was asking them. So there have been applications in other fields, and I will show you a list of applications. Geopolymer grout and binders. These are real commercial applications. Geopolymer mortar systems and grouts for use in rehabilitation from the US. From Germany, Inotec inorganic binder system, geopolymer binder for foundries. From Australia, earth-friendly concrete, fly ash slag geopolymer concrete for infrastructures and buildings. From France, high-temperature structural geopolymer composite material for automotive aircraft industries. From Ireland, heated geopolymer composite tooling for manufacture of large composite structures, aerospace, wind, mills, energy. From France, Airbus aircraft conducting geopolymer carbon composite. From Schlumberger, pumpable geopolymer formulation for oil field application. From Rockwool, Australia, geopolymer Rockwool briquettes used to recycle unused fibers. From France, method of preparing the controlled porosity geopolymer for catalysis and filtration. From UK, extruded geopolymer frame profile for window and doors. From Singapore, precast geopolymer panels. From China, geopolymer fireproof composite panels. These panels used in London would have saved lives. From Russia, 3D printer for buildings development and 3D printer with a fast-setting geopolymer concrete. From USA, geopolymer ceramic composite for high temperature. From USA, geopolymer coating for organic polymer substrate. From Sweden, composition for sustained drug delivery comprising geopolymeric binder. From Germany, fire-resistant geopolymer paint. From Germany, very resistant and acid-proof rigid anti-corrosive geopolymer coating for the protection of surfaces on metallic and mineral bases. From Czech Republic, geopolymer sand binder for cores in foundries. From the Netherlands, geopolymer composite siding and facade cladding. From USA, nanoporous geopolymer composite for use in water treatment as an absorbent for the removal of arsenic. From USA, geopolymer foam cement for lightweight and fireproof applications. From Czech Republic, geopolymer binder system for foundries. From Canada, geopolymer concrete made out of mine tailings. From Belgium, LTGS brick, low temperature geopolymer setting. From Australia, geopolymer concrete pipes. From USA, geopolymer blocks made out of clay, geology, rice husk, lime, and slag. From USA, geopolymer concrete quartzite fillers for acid-resistant applications. From Finland, solution for water purification with our patented geopolymer nitrogen removal absorbent. From United Kingdom, Sile Matrix, a specialized geopolymer technique for encapsulating various radioactive waste streams. From Brazil, decorative architectural geopolymer binder panels for inside and outside. And from France, geology applications. So there are a lot, and it is only the tip of the iceberg. It is interesting to look at how it was at the beginning, the number of people who were working. This has been our first geopolymer conference in 1988. And this is what we have today. The number of institutions working on geopolymer generates an exponential increase of paper published each year. 91, this is my first official scientific paper published. That is the reference for a lot of published scientific papers. 91. What we have here, I no longer continue. It is no longer interesting to plot. This is only the keyword geopolymer. This increase, exponential increase, generates amazing news on the internet. For example, we became aware of the forthcoming geopolymer conference for cement and geopolymer concrete in Kuala Lumpur, October 12, 13, 2017. I was struck by the number, 19th International Conference on Geopolymer Cement and Geopolymer Concrete. Since this is the 9th Geopolymer Camp, so I look at Google, and I found we had Kuala Lumpur, then we have Prague, 2017, 19th International Conference on Geopolymer. Then we have Istanbul, 2000, 19th International Conference on Cement and Geopolymer. Then we have St. Petersburg, 19th International Conference on Geopolymer. Is it a fake conference cycles? So I continue and discovered that there had been in Lisbon, April 67, the 19th International Conference on Geopolymers and Ceramics. So I look at, had the program presented, and I just, assessment of germination loss due to dusty cotton bug Oxycenus institute in relation to cotton boll stage and bug authenticity. And as a result, I continue, session 1, session 3, types of handmade dolls in Turkey, program of a geopolymer conference. Then look, there's a conference scheduled for Tokyo, October 11, 12. 19th International Conference on Geopolymer Cement and Geopolymer Concrete, Tokyo. St. Petersburg, 19th International Conference on Geopolymer Concrete. So I look at the International Scientific Committee list. And these are names that belongs to real, these are real names. And I continue and look at, oh, I know this name, Rohit Kumar, National Institute of Technology. He is on the list of participants. And he could not come. I wrote to him, and he answered, no idea. I have never been contacted by these people. This is fake. I continue my lecture and looked at the list, and I found Olesia Mikhailova. She was here. Ah, welcome. So you understand now, beware of fake geopolymer conferences. Success now today generates amazing news on the internet. Organizations such as WASET run fake conferences in order to make profit with registration fees, 450 to 500 USD, often under the names of real conferences. I'm confident that all researchers and members of the geopolymer science community will immediately realize that WASET's conferences are void of any scientific value. Please spread the word among your contacts so that nobody mistakenly participates to such fake conferences. And it is not only geopolymer, there are all topics are the subject of such fake conferences on the internet. So my state of the geopolymer has 4 parts: geopolymer science, geopolymer technologies, geopolymer cement and concrete, and geopolymer and archaeology. For geopolymer science, I just recall my campaign about why alkali activated materials are not geopolymers, because alkali activated materials are not polymers, they are just hydrate and precipitates. They cannot be called geopolymers. These are two different, very different systems, and it is a big scientific mistake to use both as synonyms. Alkali activation is the wrong terminology for geopolymer. Last year, I said, well, I think this would be my part 3 and the last one. But I have to put a part 4 that is totally different. This one is on legal and patent issue. Why? During my webinar on spring, I received this email and the question. I did my master thesis on geopolymer cement for oil well cementing with focus on high temperatures, waiting an offer for geopolymer concrete, PhD from UTS, this is in Sydney, interested to know how much room for new patents is available. Many companies are asking me. I take you an example on geopolymer cement and on a trial patent lawsuit at the European Patent Office involving the company Red Lion Cement Technology Limited, the UK-based company to which we assigned some of our geopolymer patent, geopolymer cement patent, versus famous chemical company, world chemical companies, PQ and BASF. We filed our patent in 2006, and we got it granted and issued in the US in 2012. That is 6 years later. Title, Geopolymeric Cement based on fly ash and harmless to use. The abstract reads, geopolymeric cement based on aluminosilicate fly ash and of class F, which, contrary to the prior art, are harmless to use and harden at ambient temperature, favoring their use in common applications in the construction and civil engineering fields. We are using a hardener based on silicates that have a SiO2-M2 ratio greater than 1.28, preferably greater than 1.45, that we classify as being user-friendly. The European patent was granted earlier in 2010 with the same titles. It was written in French, but in Europe you have the English titles, Geopolymer Cement, based on fly ash and harmless to use. So it was issued, granted in 2010, but in Europe there is a small particularity. There is a 9-month grace period, and during this grace period, anybody may oppose the granted patent. And on the precise last day of this grace period, the two big chemical companies, BASF and PQ Corp, presented an opposition to the patent. Why? Because the opposition was based on alkali activation, meaning it is geopolymer. And meaning, because it is simple alkali activation, it is public domain and it is not patentable. The European Patent Union Tribunal set a judgment in 24 November 2014 and declared, this was the public hearing, that the granted European patent was valid. BASF did not recognize this judgment and presented an appeal of decision, repeating the claim, alkali activated material equal geopolymer, that is public domain, and it is not patentable. So the public trials was set for the date January 23, 2017. This is an official, very important board of appeal, as I said, to happen in Munich, in Germany. They were presenting an old Soviet Union patent that was filed in 1981 and published in 1983. And one of the inventors is those who are involved in alkali activation, our friend Pavel Krivenko. The abstract reads, binder comprising granulated blast furnace slag, water glass, and fly ash, characterized in that with the object of increasing setting time, enhancing strength, and reducing bulk weight. It comprises its component in the following ratio: granulated furnace slag, water glass, fly ash. But they are using a sodium silicate with a molar ratio of 1.0 that is corrosive, therefore as it is user hostile. So the Board of Appeal of European Patent Office met on January 23, 2017 in the morning. I could not attend this public hearing, I could not be there, because I was in Florida. Professor Kriven here had organized the Geopolymer Conference seminar at Daytona Beach at that time. And on January 23, at 11 o'clock in the morning in Munich, our patent attorney called me in Florida, that was at 5 in the morning, and she said the appeal is rejected, all BASF claims were defeated, European patent is valid, that is, alkali activation AMN lost against geopolymer. So we small guys from geopolymer win the patent battle against these giants, BASF and PQ. This is what you have to know. And it is important to follow and to spread the news. So the basic chemistry is in public domain. Alkali activated materials are not patentable. Geopolymer materials are patentable when they are based on new science. For example, if you take Metakaolin, you try to understand its chemical reactivity, you understand its exothermicity. You read my book, chapter 8, in Geopolymer Chemistry and Application, and you will apply nuclear magnetic resonance spectroscopy to discover a lot of things. This is the nuclear magnetic resonance spectroscopy of silicon and of aluminum, of Metakaolin, and we have 3 species, what is called Al6, Al5, Al4. What are these species? Usually, for majority of cement scientists, mineralogists, and the likes, this is how we represent Al6. This is the hexacoordinated configuration. This is the tetragonal configuration for Al4, and this is the pentagonal configuration. And these geometrical shapes must provide a chemical reaction. So you cannot understand what is coming from this representation in terms of chemical reactivity. Because in fact, what we have, when we are making our Metakaolin, we are dehydroxylating the OH groups. This is the silicon chain, and these are the side groups, ALOH, LOH, and we have interdehydroxylation. 2 OH from neighboring aluminum are dehydroxylated, and they build the oxide. This is, from a chemical point of view, reality. So this is the first oxide that we get. But there is another route. The second route is when you take the water from the 2 OH that belongs to the same aluminum atoms, and you get the intra-dehydroxylations, that is polysiloxane and alum-oxyl double bond. So you understand that this one is more reactive than this one. And if you look back to the Metakaolin nuclear magnetic resonance for aluminum, then what you find is Al5 has this chemical molecular structure which shows the reactive sites, alum-oxyl. And you see here the aluminum is coordinated physically close to 1 oxygen, 2 oxygen, 3 oxygen, 4 oxygen, 5 oxygen. That is, it is penta-coordinating, but it is a physical, a geometrical behavior parameter. It is not a chemical parameter. It doesn't mean give any information about the reactivity of the system. For Al4, we have the aluminum, that is, we have the groups, oxygen, aluminum, oxygen, this is the oxide, and the aluminum is surrounded by 1, 2, 3, 4 atoms of oxygen, so it is tetra-coordinated, but the aluminum is still trivalent, and this one, chemically, is less reactive than this one. That is to say, in the alkaline medium, this will react practically immediately, and will take more time. So we'll have several steps. Al6, this is the remains of oxidrils in the molecule. We never get all the water out in Metakaolin. It contains between 10 and 30% of the oxidants that are still there. They need more time and higher temperature. And this is the aluminum. It is surrounded by 1, 2, 3, 4, 5, 6. It is hexa-coordinated, but the aluminum is still trivalent, but has 2 OH group. And these 2 OH group behaves differently than this oxide and behaves differently than this one. It takes more time to interact to make a geopolymer. So we will have 3 steps. And depending on how it has been manufactured, you'll get more from one, less from the other, and this is what you have to know. You have rotary kiln, you have flash calciner, multiple host calciner. You have a presentation this, after my talk on that topic. So for the rotary calcination, that is the one that is in rotary cement kiln, we have very high amount of ALOH, high amount of aluminum oxide 50%, ALOL oxide only 15. If you compare to the flash system that is super rapid, you have less ALOH, more ALO, and a little more of the reactive elements. If it is the vertical oven, then you have also less ALOH, aluminum oxide 49, and ALOL 27. Last year, we started here with university and with Professor Pelgris that is here. Please raise your hand. Very precise study on the Metakaolins. And we presented our first results that you can find as a PDF on our internet site, which was a pragmatic approach in designing a high-performance geopolymer ceramic for the 3D printed mold from theory to practice. And we applied the reactivity test, that is, Metakaolin is exothermic in the alkaline medium, and we are measuring the increase of temperature that we get when we put the sample in an oven at 80 degrees C. So we have here the reference, that is the blank sample, and here it is the sample that will be tested, and this is what we get. We have here the graph, the time, the temperature increase, the oven temperature is 80 degrees C, and we are testing 10 commercial Metakaolins. And you see that they are behave all differently. You have the blank sample. This is the one that provides the temperature of the sample in the oven. We measure it, and it reaches 80 degrees C after more than 1 hour, whereas some of the Metakaolins develop temperatures practically as high as 110 degrees C within 18 minutes. This is exothermicity. Others are slower. Is 20 minutes. So you have the Archaeological 1200, Metastar, Power Pose. They are slower. Metamax is a little slower. Another Archaeological is slower. And there are some other so-called Metakaolin that practically did not harden, did not exotherm. So they are presented and sold as Metakaolin. This is essentially for cement, Portland cement applications. But you see here the test that shows, here we have a lot of these special oxides, double bond aluminum oxide. Here we have less, and we continue where less and less. It needs more time to reacts. This year, we continued the study with 2 students, and there will be a presentation this afternoon where we continued designing high-performance Metakaolin-based geopolymers, polysilicate siloxane KPS binders, from theory to practice. So, second part, geopolymer technologies. There is chapter 23 in my book, what I call the geopolymer route to high temperature ceramics. This will be, we will have 2 keynotes just after my talk on that subject. One will be presented by Professor Walter Kriven. She and her teams have developed Metakaolin-based geopolymers that can be converted to high-strength ceramic materials on heating. We have sodium geopolymers that crystallize into nepheline and are on heating to 900 and 1100 degrees C. Potassium geopolymers crystallize into leucite. These are very well-known chemical ceramic materials on heating to 900 to 1200 degrees C. They crystallize, that is, they are formed at low temperature, and then they continue and crystallize. Cesium geopolymer crystallize into pollucite on heating at around 1050. These ceramic materials have unusual properties such as refractoriness, relatively low density, and high fracture toughness. Their properties enable geopolymer ceramics to be used as reinforcement in thermal barrier coatings or to increase toughness in glass ceramics. They continued with a very interesting study that was published in 2016, synthesis and characterization of silicon carbide powders converted from Metakaolin-based geopolymer. So they are doing a geopolymer mix and are in situ manufacturing silicon carbide. This shows here an SAM macrograph of potassium geopolymer and 18 carbon made 2 hours after being fired to 1500 degrees C in flowing argon with needle-like morphology. This is what they got here. They have done it with no extremely high temperature. Instead of 2500 degrees C, 1500, and you get your silicon carbide. We will have a focus session on geopolymer composite, and I started to publish in May 2016 the 3rd virtual journal on geopolymer science that was dedicated to reinforce geopolymer composite. That was a critical review of what has been done so far. What we have geopolymer fiber composite. These are carbon geopolymer matrix for fire and heat resistance, and this is, I guess, aluminum fibers compared to carbon epoxy composite is burning, and the geopolymer matrix with the carbon resists the flame of a torch at 1200 degrees C without any problems. If we compare the time to flashover, that is the time that is after which the organic plastics are self-igniting because of the fumes in a fire. The thermoset, these are the major plastics that are used today, ignites after 12 minutes. That is, when you have a fire in a room, after 12 minutes, anything that is in plastic made out of that will self-ignite. You have no time to escape. They have progresses with phenolics, you have more time, and engineering and a geopolymer will never self-ignite. This has been a beautiful study that we made in the US with the Federal Aviation Agency for cabin safety for aircraft. Professor Criven will present the geopolymer-based composite, essentially on eco-fibers, biofibers. So this is just an example of the result that she got. This one is remarkable with a special fiber, Manila hemp. They got 52 MPa strength and she will present it this afternoon. Third topic, geopolymer cement and concrete. There's a news from Australian Slag Association. The rise of geopolymer concrete research binds us together. The exponential rise in geopolymer research is capturing industry interest. Published research papers covering geopolymer concrete, such as different mixes, methods, and applications, are challenging the conventional use of concrete. The association's involvement in the Cooperative Research Center for Low Carbon Living Research project is just one example of how much focus is being placed upon much geopolymer research. As geopolymer concrete knowledge increases, so does its interest. The increasing amount of research, technical and commercial papers being produced and published support this view. Geopolymer concrete is becoming more widely accepted within the industry and for the promotion with reduced CO2 benefits. My recommendation to the slag industries. We have with slag the same problem than we have with metakaolin. That is, each slag tested is reacting differently. So if there's something to do by the slag industry is to try to understand why they are reacting differently and to do the work that we have been carried out here with Metakaolin, or to ask us to do it for them. Because formulas that have been done in one country with one type of slag are difficult to transfer to another country where the slag is different. Knowledge on slag is poor. When I told you that the knowledge will generate new patents, this is an example. There's been a news in Journal of Petroleum Technology. University consortium prepares for spike in decommissioning of oil platform, offshore platforms. For those who are not fluent in English, spike means high increase. It will be more and more and more decommissioning. The Consortium for Decommissioning and Abandonment at University of Texas at Austin is a response to the growing number of onshore and offshore wells, platforms, and infrastructure that are approaching the end of economic viability and soon must be plugged and removed. Toward those ends, university researchers have developed several systems, including geopolymer cements. Tests on the newly designed cement also indicate significant self-healing properties. The system's designers are scheduled to present a paper on the geopolymer cement on March, a Society of Petroleum Engineers, during conference in The Hague, and this is the paper that they presented. It is based on fly ash. There is an interesting patent that has been published this year, published, not granted, in the US by a friend from Louisiana Tech University. The abstract, a method of controlling the setting time of a geopolymer by coating aluminosilicate particles with nanoparticles to slow the geopolymerization reaction, the coating effect, and so forth. What it is about, so they take a geopolymer paste samples, were prepared by premixing for approximately 30 seconds, 20 grams of fly ash with halloysite nanotubes in an amount that was 3% of the fly ash weight. That is, they have the fly ash spheres that are recovered with a very tiny coating of halloysite. Result, geopolymer paste control, setting time 18 minutes, final setting 25, 3% halloysite instead of 18 minutes, 70 minutes setting time. Wonderful. Instead, with 6% halloysite, 175 minutes, or 47 or 170. So this is very interesting. But I wondered, why do they need to slow down the reactivity of fly ash when we know with our fly ash that it does not set at room temperature? So I was puzzled. I did not understand what they were writing. And it is also a subject of concern, the way how patents are written by patent attorney. They generalize a very particular item. So I went back to the text and read it carefully. Geopolymer paste samples 1 hour were prepared with premixing for approximately 30 seconds, 20 grams of fly ash. Example, Dollet Hills fly ash. What is that? Ask Google, and Google gave the answer. This is a class C fly ash. The class C with high amount of calcium oxide. We know that it flash set. We know the problem of those countries that only have class C fly ash that have a setting within 15 minutes. For example, in Malaysia, there have been a lot of studies. I remember Nuruddin presenting papers here on how to retard the setting of class F. So, but here, you have the claim. They claim that every aluminosilicate material, like all fly ashes, F, C, anyone, are covered by this patent, when it is only valid and used for only one particular class C. So a patent that is so general is very easy to destroy. But this is how patents are written, essentially in the US. So my last word on, I hope, on alkali activated materials versus geopolymer cement. I repeat things that are well known, I hope now. This is the chemistry of Portland cement hydration. You are dealing with small molecules. This is a monomer. This is a monosilicate of calcium. This is a simple small molecule that is hydrated and generates the formation of a dimer 2Si, calcium disilicate hydrate. This is the CSH of the cement scientist. Period. This is geopolymer chemistry. It has nothing to do. You have the polymerization, the polycondensation of molecules that build a network. And this is a polymer. But cement scientists that are accustomed to Portland cement terminology with their calcium silicate hydrate CaO, CO2, H2O, that is CSH, when tackling so-called alkali activation or geopolymers in their mind, substitute the calcium with the sodium and the potassium, and are starting to make a big chemical mistake. Calcium is known to be insoluble in water. So you may have a calcium silicate hydrate. You don't care about the water, the calcium still remains on place. And you may use this terminology. But if you replace the calcium with the sodium and the potassium, as they are doing for geopolymer, sodium, aluminum, silicon oxide, sodium, aluminosilicate hydrate, the sodium is very soluble in water. That means if it is an hydrate, all the sodium will be leached out, will move. So they call it NASH, which is totally wrong. And it is a very crucial, fundamental mistake from a scientific point of view, and that induces and generates all wrong behavior and very wrong thinking about what is good and what is geopolymer. Same for potassium. Potassium in an hydrate will practically immediately migrate, be leached out. So all this terminology that you'll find in papers, essentially those written and published by a well-known journal called Cement and Concrete Research, where you have all geopolymer NASH cache, are totally wrong and inducing wrong information to the community who want to develop something. So according to alkali activating materials cement scientists, geopolymer is a type of alkali aluminohydrate, NASH cache, nothing else. It is wrong. Geopolymer results from polycondensations of well-defined monomers, like this one, SiL 3-1. This is the polysilate disiloxo cycle that polycondense and build the first ribbon. Oligomer, it is a small molecule that will, can be called cache. You have the potassium, you have the oxidrils, and you have some water, and you have the KOH. So it is the calcium aluminosilicate hydrate. But it is the first step of geopolymerization. It is not the end result, because it continues to build the three-dimensional network. If you stop here, of course you have cache. You have something that has 1 MPa strength, put it in water, it will dissolve, be destroyed. But this is not what we are doing. We continue polymerization, and we create a three-dimensional network. And when we look at nuclear magnetic resonance spectroscopy, this is what we have for the aluminum. The aluminum is surrounded by the silicon and has its potassium strongly attached to it. It will not move. This is what nature has done with all the feldspars, with all the granite, with all the basalt, with all the stones. They are made according to the same structures, and they are still there, millions of years. It is not cache, it is not NASH. So if you want to have cache and NASH product, you look at one patent that has been granted in the US in 2016. Alkali metal ion source with moderate rate of ion release. So you extract the cation, the potassium and the sodium, and method of forming. There is a growing need for alternative sources of alkali metals, such as, but not limited to, potassium, traditional potassium fertilizing agent, making local manufacturing of potassium fertilizer increasingly attractive. Therefore, a need exists to produce a source of potassium ion that releases the nutrient, that is the potassium cation, at a moderate rate, lower than the infinite dissolution rate of a traditional salt, but faster than the rate generally exhibited by naturally occurring minerals. What we have a cache gel here. They are producing, manufacturing a cache gel, but this is their target to get, and their claim, the method wherein the weight percent of cache gel of the alkali metal ion source is between about 10% and about 100%. For what purpose? To make a fertilizer, to have the potassium cation coming out in earth with water. This is logical to have this type of terminology. And who is filing for such a patent? Massachusetts Institute of Technology, MIT. So MIT is not claiming that cache is geopolymer. MIT is working on cache as a fertilizer. Do you understand? This is the reality. This is NASH, sodium aluminosilicate hydroactive alkali activated materials, with all blooming, all the sodium coming out. This is a wrong mix. This is geopolymer ceramic. This is geopolymer concrete. This is slag fly ash based geopolymer concrete. I will finish my keynote with archaeology, and I'll present, we have a third session that will be on Wednesday, not this evening, where we will have on ancient Roman concrete. But here I want to present some of the work that we have made on and presented at the 11th International Congress of Egyptologists in 2015, on non-destructive analysis on 11 Egyptian blue fine styles from the 2nd and 3rd dynasties. That is 2700 BC, 4,700 years ago. We also presented this at a seminar at the MIT in October. What it is about? This is the first step pyramid bout in Egypt, 2700 BC, and in the subterranean galleries, they were adorned with more than 35,000 fine styles that look like this, that you find in the museums. It is told that this is the glazing is resulting from the efflorescence of the migration of salts that are then fired at 850 degrees C, and this is called the turquoise blue glaze. When you look at what is in the museum, you'll see also this. You have blue, you have green, you have black, you have brown. So we tried to understand what was going on here. Since for me, manufacturing 35,000 tiles, this is an industry that requires a lot of kilns, and archaeologically they were not found. And this is a problem, how to do it. So we presented in 2004 our first result on the subject, That was why Djoser's, this is the first pyramid, blue Egyptian fine styles are not blue. Manufacturing Djoser's fine style at temperatures as low as 250 degrees C. The geopolymer technology allows to do it at low temperature. And what we made a replica of this coloration with a synthetic turquoise, and we got animals at 250 degrees C that was blue for potassium, that was green for sodium silicates, or that was black if the samples were heated above 300 degrees C. We received some years later a mail from an antiquarian that has a collection of these tiles, and he asked a renowned laboratory in Oxford to make thermoluminescence analysis for datation of the ceramic that are supposed to have been fired at a temperature of 800 degrees C. The thermoluminescence analysis requires that the ceramic has been fired at least over 500 degrees C. So they made the analysis in Oxford, and this was the answer. It is not possible to issue a result for this piece as the sample is too low fired and lacks radioactive inclusion. We are therefore unable to complete our analysis and draw any conclusion regarding its age. So you have a genuine 4,500 years old artifact that is supposed to be a ceramics fired at 800 degrees C, and when it is analyzed, it shows that it is not. And these experts at Oxford knows that, but it is not published. They are quiet. I asked them by mail, why are you doing this? And they answered, well, we don't have any answer. We don't know why. Well, all the samples, all the tiles that we are getting for datations behave in the same way. That is, they are low fired. This is contrary to what is taught, what is you see in the museums, what you see in the books, and they remain quiet. This is Egyptology science. They remain quiet because they have no answer. So the antiquarian, Lucien Viola, contacted us since he had read on the internet our paper presented at the Egyptology conference was published. He found us and said, oh, these are people who are claiming that they can do low temperature ceramic and tiles. He contacted us, and this is part of his collection, and we got several samples and we started to analyze them, and we found that we had a glaze that contained silicate, copper, magnesium, calcium, aluminum, sodium, chlorine. Oh, we suspected that we were dealing with a material that was based on this guy, copper chlorine, that is the atacamite, famous also in painting. This is a pigment. And we started to look at the tiles. It is an hydrate that does not exist if it is fired at 800 degrees C. It is totally destroyed. It is turned into copper oxide. It cannot be there. So we selected several tiles. These have been published, but I am only presenting one very important tile that we call it our Rosetta tile that provides the answer. This is the front glaze, and this is the back of the tile. These tiles are 6 centimeter big length. These dimensions So the glaze on the front is uniform and has made of silicon, and you have copper chlorine, atacamate hydrate here. Then we looked at the backside, and we found something very strange. If we get close up, we have here the white core. We see what it is. Then we had a first glazing. This is an efflorescent glazing. Then we had the first paint and the second paint. 3 layers. 1, 2, 3. So we look at this under the electron microscope. The white body, this is our quartz element, very fine. This is 100 microns. And we have a binder. And this binder has the same composition, chlorine, copper, same composition as the glaze. So it is the binder for the glaze that is used for making the tile. But it is the result of self-glazing. This is soluble, and it efflorescence first drying. So it is a type of silicate geopolymer-based binder that hardens and migrates during heating, and it glazed at 250 degrees C. Then we looked at it, and we saw small spheres, very, very precise spheres, close up, and we looked at and had silicon, copper, chlorine, same makeup. It is overfused material that makes droplet, small droplet because of your fusing. So we look at then at the layer number 3, that is green, number 2, pardon, that is green, and we had a different element, lot of copper, lot of chlorine, but a lot of sodium. In fact, we found sodium chloride, salt, and the same blue, mineral, atacamate, the hydrate. And then we made a close-up and found that it is expanded. It is a foam. So it is a foam that results from the dehydration of the material. It is a water-based silicate that contains the geopolymeric reaction, and we know in the lab we make our foam at 200 degrees C, 250 degrees C. The water vapor wants out, the softening of the matrix, and you create a foam. This is what we have, a foam. So we looked at layer number 3. This is the blue one. So we have a glaze, smooth, and the close-up you see holes, very small holes that in fact was coming from underneath. It is the vapor that was escaping during the foam formation and going through the so-called glaze, going through when it was in the liquid phase and hardening. We have silicon, copper, chlorine, no sodium. Sodium is there and provide the green color. This is what we had also found in our first study. In the presence of sodium, we get green color with copper. And when there is no sodium, it is blue, like turquoise blue. So the conclusions. The production of 30,000 tiles is feasible in an open garden fire at low temperature below 250 degrees C. The glaze is a coating comprising 3 successive layers. One, it is the efflorescence, low temperature self-glazing. Then we have a second layer, that is either we found calcium sulfate on some tiles, or we found calcium phosphate on the layer under the glaze, or we found the green geopolymeric silicate layer with paratacamite. And the third layer, that is the low temperature geopolymer enamel, what is the only shiny external layer that contains the blue paratacamite and calcium, silicon, so forth, a formulae that we have to discover, and it will bring new knowledge on geopolymer science. This is the end of my state of geopolymer for this year. Thank you for your attention.